Hi guys, and welcome to Chapter 13. For Chapter 13, we're going to be talking about the atmosphere, the layer of gases that surround and envelop the entire planet, as well as pollution and ways to control air pollution specifically. So for today, this lecture, we're going to be talking briefly about the atmosphere, what it does, why it's important, the difference between weather and climate, and some of the different features of the atmosphere that support our long-term climates as you look from the equatorial latitudes all the way up to the polar latitudes. So the atmosphere, going back again to our recap from Chapter 2, are the layer of gases that surround and envelop the entire planet. And the atmosphere is important for a number of reasons. First and foremost, it provides the air we breathe and allows us to survive. It also dictates weather and climate, two definitions of which we're going to go over in a second. It shields us from meteors and meteorites, so things that are trying to bombard us from the atmosphere normally burn up due to all of the friction in the atmosphere, and so they're no longer allowed to come into contact with the solid part of the earth. And it protects us from harmful solar radiation, something we're going to go over in depth when we talk about the ozone layer. Now, the atmosphere is primarily composed of nitrogen. About 78 to 79% of the entire composition of the atmosphere by volume and by mass is nitrogen. And then about 21% is oxygen, so the air that we breathe, O2. And then finally, about 1% of the gases in the atmosphere are composed of minor gases, things like neon, helium, hydrogen, xenon, as well as variable gases such as water vapor, which can fluctuate, carbon dioxide, which can fluctuate, methane, nitrous oxide, ozone, and chlorofluorocarbons. These last variable gases are going to be of particular importance, specifically because they contribute to the greenhouse effect, something that we'll be talking about in later lectures. Now, the atmosphere is layered, and you're going to need to know the first two layers in particular, but all of these layers play an important part in the atmosphere's function and how it relates to us as humans, as well as other organisms on the planet. First and foremost, you have the troposphere. The troposphere is the lowest layer of the atmosphere. It's the bottom layer, so it's the first 11 or so kilometers or 7 miles above sea level, and it's responsible for the Earth's weather as well as the Earth's climate. A lot of weather, or most weather patterns, are completely dictated by the troposphere. Going above that, water vapor can't really ascend beyond the troposphere. It's too dense, and so the upper layers don't really play a role in the weather function or the climate function of the atmosphere. Now, next, going up, you have the stratosphere, which is between 11 and 50 kilometers above sea level, and so this is where the ozone layer exists. And the ozone layer is really important because it shields us from harmful UV radiation. Again, we're going to be going over the ozone layer in detail here in one of the next lectures coming up. But for now, just know that the stratosphere houses the ozone layer. It's very important because as a result, the stratosphere shields us from harmful UVB and UVA radiation. And it's a little bit drier, a little less dense, and there's not as much vertical mixing simply because there isn't a lot of water vapor and it's a little bit farther away from the ground and sea level than the troposphere. Next, you have the mesosphere, which is about 50 to 90 kilometers above the Earth's surface, and this has lower air pressure, colder. It's getting colder with altitude. And then finally, you have the thermosphere, which is the very highest layer, and that's going to be between 90 kilometers to 500 kilometers. It's just going to be the outer reaches of the atmosphere in general. Now, what's really important here is going to be the troposphere and specifically how it dictates weather and climate. Two things are very important for us as organisms. Basically, weather and climate involve the physical properties of the troposphere. And these are going to be things, variable factors such as temperature, pressure, humidity, cloudiness, wind speed, etc. And it's very important to note the difference between weather and climate. Weather is atmospheric conditions that are very short-term in length. So these are going to be over very small geographic areas, basically as a weather band or weather storm moves across a given area, and it's going to be over very, very short time intervals, things like hours to days, maybe a week or so at the most, if it's a particularly strong hurricane or some really bad weather, for example. Contrast that then to climate. Climate is very important because climate are long-term patterns of atmospheric conditions across a very large geographic area, and these are going to be over very long periods of time. When you think of weather, think of days to weeks. When you think of climate, think years to decades to millennia. Now, I threw months in there just because climate can vary seasonally. However, normally climate operates on the scales of years to decades to millennia. Now, it's important to note that the sun drives weather patterns in climate as well as patterns in weather globally. And this is because the sun delivers all of the excess energy that is allotted to the entire planet. And so while 70% of the energy is absorbed by the atmosphere and the surface, meaning that 30% is reflected outwards, it dictates a lot of weather patterns just because it provides the energy for weather to function. So the sun is the primary driving force of all weather on the planet because the sun provides almost all of the energy that the planet receives. Now, most of this energy actually passes through the atmosphere and actually hits the surface. So it completely goes through the atmosphere with very little inhibitions, and then it hits the surface of the Earth, the solid and the liquid sections of the Earth below the atmosphere. Now, what happens here is that this energy that the sun radiates into the planet is not heat energy. It's primarily going to be UV radiation and several forms of light. Now, this radiation is then absorbed completely by the hard surface of the Earth and then re-emitted as thermal or heat energy. So it takes the energy or the radiation from the sun and then re-emits it as heat. So as a result of the surface of the Earth re-emitting that thermal energy out into the atmosphere, the troposphere actually heats from the bottom. The troposphere will heat from the bottom basically because the bottom is the layer that's exposed to all of the thermal energy right at the surface of the Earth, and then this troposphere will gradually cool down as you move higher and higher up in altitude. Now, this is going to be one of the reasons that higher altitude areas like mountains, for example, are going to be a lot cooler in temperature than areas close to sea level, just because they are farther away from the primary re-emission of thermal energy. Now, contrast that then with the stratosphere. The stratosphere actually is cool at the bottom and gradually heats as you move higher and higher. And this is primarily because the ozone layer exists at higher altitudes in the stratosphere. Basically, the area that's going to be absorbing any sort of radiation in the stratosphere is going to be the ozone layer. And again, we're going to get to that in a little bit. But what happens is the ozone layer at very high areas in the stratosphere absorbs a lot of the UV radiation and re-emits thermal energy, similar to how the surface of the Earth does so as well. So in contrast to the troposphere, the stratosphere heats with increasing altitude while the troposphere cools off with increasing altitude. Now then, after you get from the stratosphere to the mesosphere, because the ozone layer is in the higher altitudes in the stratosphere, you have heat from the ozone layer moving into the bottom layers of the mesosphere. So the mesosphere also heats from the bottom and cools off gradually as you move higher and higher. And then finally, the thermosphere heats up radically simply because it is now completely exposed to the sun's rays, and it is the area that also captures a lot of excess radiation and keeps it from hitting us at the bottom of the Earth. And so the thermosphere heats up very drastically in contrast to the other layers, simply because it is exposed to the bulk of the sun's radiation. Now, the reason these changes in temperature with regards to the layers of the atmosphere, and particularly the troposphere, are so important is because these changes in temperature are one of the main drivers of weather and climate around our planet. And this is done through a process known as convective circulation. Basically, convective circulation involves the cyclical movement of cold, moist air becoming hotter, expanding, and then releasing rainfall, and then falling back onto the Earth where it can repeat the cycle over again. Essentially here, what's going to happen is that cool, moist air is near the surface of the Earth, primarily because that is where a lot of evaporation from water takes place. Now, as this air sits near the surface of the Earth, because the Earth heats from the bottom, remember that the surface of the Earth re-emits heat radiation, that moist air at the bottom of the troposphere heats up very quickly. Now, because warm air expands when it is heated up, essentially what happens is that this warm air is now less dense than the cooler air above it. Then what happens here is that warm, moist air gradually heats up and expands and then rises into the higher layers of the troposphere. Once it has reached higher layers in the troposphere, remember that the higher altitudes in the troposphere are very cool. That warm, moist air essentially condenses and cools off. Once it condenses, it can no longer hold in that water vapor, and so rain will then fall from the top of the troposphere and hit the Earth. So this is how rainfall patterns are driven. Then, once the air has cooled off sufficiently, it becomes more dense than the air below it, and because it is more dense, it sinks back down again, where it can pick up more moist water or from water vapor and heat up all over again, so the cycle can continue. However, occasionally a layer of cool air can actually get wedged underneath that warm air, particularly in wintertime where there's not a lot of solar radiation being re-emitted out as heat energy at the bottom of the surface. So basically what happens here is that the layers are flipped, whereas traditionally you have hot air on the bottom of the troposphere right by the surface of the Earth, and then it gradually gets cooler as you go higher and higher. In the instance of what's called a thermal inversion, that cycle is flipped. So in this case, the cool air is actually right on the surface of the Earth, and the hot air is actually above it. And because of this, the hot air is going to be above the cooler air, and so there's no longer going to be that convection cell that we just talked about. So there's no longer any cycling. And when this inversion layer happens, this band of cold air where the temperature rises with altitude, there's no longer any mixing whatsoever, and so the cool air just sits at the bottom. And what happens here is when there's a lot of pollution in that area, it almost acts as a cap. Whereas traditionally, if the pollution was emitted at the bottom of the surface and it would warm up and gradually rise to the top and away from people to breathe, this cool air at the bottom cools off the pollution right at the source and keeps it trapped right in the area where people are exposed to it and people breathe. In instances where a city such as Los Angeles is surrounded by a mountain range, meaning that the trapped air can't move away horizontally as well as vertically from this area, that means that it can actually just stay in this cap right around the base of the city and cause horrible breathing problems until that thermal inversion layer is flipped back and begins to operate again normally. Now, we've talked a lot about how these different convection cells will operate on the smaller scale in terms of weather, but they also operate on a global scale to dictate and influence climate. And they're divided into three major categories of cell based on where they are latitudinally along the globe. So the first cell that we're going to talk about is called the Hadley cells. The Hadley cells are going to operate right along the equator, and basically this is going to be your basic convection cell. So again, the warm air at the bottom of the Hadley cell will pick up a lot of water vapor as evaporation happens, and then what happens here is that warm moist air will rise as it expands and becomes less dense than the cooler air above it. As it rises, it cools off and contracts. When it cools off, it pours rain down right below the base of the Hadley cells, which is one of the reasons why the equatorial regions of the globe are very wet, is simply because all of that rainfall, as the Hadley cell operates and moves higher and higher, basically it loses all of the capacity to hold that water vapor, and so it settles out as near constant rainfall right around the tropical regions near the equator of the entire globe. Now, once that moves up, it is now cool, dry air. As the air begins to continue to cool, it becomes more and more dense, and then later on, as it moves farther and farther away from the equatorial regions, settles back in as more dense air and gradually falls to the bottom where the cycle can repeat again. So moving forward, we're going to be talking next about the mid-latitude cells, or the Ferrel cells, that operate in between the Hadley cells and the polar regions of the globe. Now, unlike the Hadley cells, the mid-latitude or Ferrel cells operate in a counterclockwise direction as a way to complement the Hadley cells. So basically, in this case, the cold air is sinking in the same place, and then the warm air is moving in opposite directions latitudinally across the globe. And unlike the Hadley cells, which were able to pick up a lot of moisture and then deposit it right on the equator, the Ferrel cells are very dry. They've already deposited all of their water at the equatorial region, and so as a result, this dry air is readily absorbing water along the surface of the Earth as it heats up. So because of this, these Ferrel cells are very, very dry, and the land below Ferrel cells are very, very dry. This is one of the reasons that we have so many deserts in the northern hemisphere right around the 30-degree latitude mark. You don't really see them in the southern latitudes because there's not a lot of land in that area, although Australia is a key example of what happens when you have a large landmass in the lower 30-degree latitudes in the southern hemisphere. There's also a lot of desert in that area, but because the majority of the landmass on the Earth is in the northern hemisphere, 30 degrees latitude north has a lot of deserts, but simply because the Ferrel cells are so dry, they don't allow a lot of precipitation. Moving farther north or farther south into highest latitudes, you have the polar cells. Now, because of this, you have a very high amount of precipitation right at the crux between the Ferrel cells and the polar cells, and this is because the polar cells operate very similar to the Hadley cells, albeit in very cold temperatures. So basically, the polar cells are going to pick up a lot of moisture as they are moving toward the equator in their convection cycle. They're very dry air, so it will pick up a lot of moisture. As it rises right at the crux of the mid-latitude cell and the Ferrel cell, it will deposit all of its rain, which is why you have very lush boreal forests right at the 60-degree latitude mark, either north or south. You have very lush cold forests simply because you get a lot of precipitation right in that area because the polar cell is dropping all of its moist air. However, in the at the base of the polar cell, at the very poles, either North Pole or South Pole, that dry air is now sinking again and looking to reabsorb more moisture. It's not depositing any. So that is why Antarctica is actually one of the largest deserts on the planet, is because even though it's very cold and has a lot of ice, it doesn't see a lot of precipitation simply because all the air is doing is picking up more moisture. It's not depositing it on the poles. So what I want you to take away from this is that polar regions are very dry. Mid-latitude at 60 degrees, either north or south, is very wet because the mid-latitude and the polar cells are dropping all of their precipitation. In the area between the Ferrel cells and the Hadley cells, where the precipitation has already been dropped and they're looking to absorb more moisture, those are where your deserts are going to be. And then finally, at the 0-degree latitude, basically the equator, you're going to have some of the highest rainfalls you'll ever see, simply because that is where the Hadley cells operate and whereas the warm air is rising and then dropping all of its precipitation. So, just to reiterate, the cells dictate global precipitation patterns. Basically, any time that warm air is rising, you're going to get a lot of rainfall. Case in point is the graphic below where we're looking at the Hadley cell. And then any place where the cells are sinking, where cool, dry air is sinking and looking to pick up more moisture, that's where you're going to have dry deserts, simply because there's not going to be a lot of precipitation as that dry air is moving down and looking to reabsorb more moisture. Now, in addition to this, cells also dictate global wind patterns, and this is through something called the Coriolis effect. Basically, the Coriolis effect is the apparent north-south deflection of air currents as a result of these convective cells. Basically, what happens is that these cells not only operate vertically, where they are rising, cooling, and then sinking back down, they also operate on a given north-south gradient. So basically, they're also operating horizontally. So it's almost like a three-dimensional cell. And so as a result, they move in opposite directions. So where you have the North Hadley cell moving up, it also moves west along the equator, and then eventually moves north as it goes forward. However, the opposite happens on the South Hadley cell. So, for example, it also moves west, but as it deflects south, and so it curves south. And so these cells will operate in opposite directions. Now, these wind patterns dictated by the convection cells are basically what drive the trade winds and some of the permanent weather patterns that we see wind-wise around the entire globe. So it's important to note that the cells not only dictate precipitation patterns, but also global wind patterns. Now, this is everything that we have for the atmospheric lecture. I really look forward to talking to you guys about air pollution. Air pollution is one of the positive stories in environmental science simply because we have done so much to improve it over time. So I'm looking forward to talking to you guys next about outdoor air pollution. See you then.